Let me just briefly summarize what we did in the previous class. We related control mass with control volume. The relation is called Reynolds transport theorem. Okay. The theorem stated that I can relate some extensive quantity of my system with the rate of change of that quantity, of that extensive quantity, with the rate of change of that quantity in control volume. CV eta rho dV plus integration over control surface eta rho V xyz dot dA. Okay, where this eta was total extensive property divided by mass of the system. Okay, then using mass as extensive property and assuming the flow to be uniform and incompressible, we arrived at this expression: summation over CSI V xyz dot A vector rho, for that CSI equal to 0, right, where this density, velocity of the fluid with respect to control volume and A vector corresponded to that control surface, right. Then using linear momentum as the extensive property and assuming uniform, incompressible and steady state flow, we arrived at this expression. Okay, just let me not write steady state for now. So for uniform and incompressible flow, we arrived at this expression: summation over all external forces on the control volume is equal to d by dt integral over control volume Vxyz rho dV plus summation over all control surfaces Vxyz dot rho Vxyz dot A vector over CSI. Okay, and we argued that in addition to uniform and incompressible flow, if we have steady state flow also, then the term d by dt integral over CV Vxyz rho dV is 0. Okay, so this is what we have done till now using Reynolds transport theorem. Okay, now let's come to the problem that I discussed before deriving Reynolds transport theorem. So this was the problem that I took from Fox and McDonald's Introduction to Fluid Mechanics. Let's first read the problem. So it states that water from a stationary nozzle strikes a flat plate as shown. So there is a nozzle from which water is exiting, and this nozzle is stationary. The water leaves the nozzle at 15 meters per second. So the velocity of this exiting water is 15 meters per second. The nozzle area is 0.01 meters square. So the area of this nozzle is given to you. This area is given to you in the problem. Okay. Then, assuming the water is directed normal to the plate and flows along the plate, determine the horizontal force you need to resist to hold it in place. So it states that the water flow is something like this. Okay. Now the question is, if the water flow is like this on incidenting on some plate, then what is the amount of force that you have to provide in the horizontal direction? Let's call it Rx. What is the amount of force Rx that you have to provide on this plate so that the plate is stationary? Okay. First of all, let's understand why do we have to provide some force to keep it stationary. So if you have, let's say, a plate like this and you have some fluid which is going like this and reflecting, let's say, like at some angle like this, there will be a change of momentum of this fluid, correct? Now because of this change of momentum of the fluid, this fluid will impart a force on this plate like this. Okay. Now to counterbalance that force, you have to provide some force in this direction so that the plate would remain stationary. Okay. Now if you remember, I said we can do these kind of problems after deriving Reynolds transport theorem. Okay, so let's start. So I have just copy pasted this image here twice. Okay, so now the first thing that you have to do so that you can solve the problem using Reynolds transport theorem is to define the control volume. Okay, so let's try to understand how to solve such kind of problems using different control volumes. So let's say the first control volume that I will define is like this. Okay, and the second control volume that I will define is this. All right, and let's see whether we get same answer for this Rx using two different approaches. Okay, so let's start with the first approach. So I have copy pasted this image over here. Okay, let's define the control surfaces CS1, CS2, CS3 and CS4. Okay, now since it is not explicitly written, let's assume also that the flow is uniform, steady and incompressible. Okay, if it would not have been incompressible or steady or uniform, it would have been given in my question. Okay, all right. Next, let's write Reynolds transport equations for mass and momentum. So what was the first equation? First equation was, so for you assuming these three flows, I would get, for the mass, I would get summation CSI rho V dot A in that CSI is equal to 0, and using equation for momentum, equation for linear momentum, I have summation of external equal to, okay, so now the flow is ready, so I can just, so this term is 0, okay, and the other term is summation CSI V rho dot dA, sorry, not dot A, okay. So we have these two equations, and using these two equations we have to find Rx, okay. So Rx is a force, and out of these two equations, which equation tells me about the force? This equation, right? So let's first simplify this equation for my given control surfaces, okay. So this should be a vector. Now let's take this equation, since we are required to find the horizontal force Rx. So if you see here carefully, it is written you have to find the horizontal force, okay. So since you have to find the horizontal force, let's just consider, so let's say this is x, let's say this is y, let's just consider the problem in x-axis only, okay. So we'll have F external acting along x-axis equal to summation over CSI V xyz acting along x-axis rho V xyz dot A vector. Now please note that this V xyz is not along x-axis, okay, because the vector part of this equation is given by only this term. Since this is a dot product, this won't give me the vector part, and that's why this Vxyz is the total Vxyz at that control surface CSI, okay. Alright, so I have this equation, and let's not write this bracket again and again. Now whenever I will write this, you please assume that these three or these four are in that CSI only, okay. Alright, now consider this F external along x-axis. So what is the external force along x-axis for this control volume CV? What is that? Now you may say that, oh, the system is only fluid and the force is being applied on this plate, so why are you considering F external to be Rx? It should be the force on the fluid and not on the plate. So the answer is, when I have defined the control volume, I have considered the system to be the fluid plus the plate, okay. And that's why this force on the system is actually the force on this control volume. Since the plate is the part of the control system, plate is the part of the system, okay. And please also note that the force on the system is equal to force on the control volume. This is because while deriving Reynolds transport theorem, we assumed that the system and control volume coincided at t is equal to t naught. Okay, all right. Now you tell me, what is F external in the x-axis? So is there any external force from this side? No. What is the external force from this side? It is Rx. What is the external force? Okay, so we have to take only in the x-axis. So let's, or is there any force on this control surface along this direction? No. And similarly, there is no force on this direction, on this control surface CS2. Okay. So then this F external along x-axis can be written as minus Rx, where Rx is the horizontal force that we need to find. Horizontal force to keep plate stationary. Okay, so this is minus Rx I hat, since it is in negative x-axis, okay, equal to, okay, so now we have to consider the control surfaces. Okay, so if you see here, only the terms with Vxyz in x-axis, where Vxyz in x-axis is non-zero, only those terms will contribute in this equation and the other terms will go to 0, right? Okay, so I have 4 control surfaces, CS1, CS2, CS3 and CS4. In all these control surfaces, out of all these control surfaces, what would be, or what are the control surfaces that will contribute in this equation? So the answer is, on this control surface there is a Vx. On this control surface the flow is like this, okay, and on this control surface the flow is like this, and on this control surface there is no flow. Okay, so the only control surface that has this Vxyz in the x direction non-zero is CS1. Okay, so only CS1 will contribute to this term and others will be 0 for when I have taken the x component of this equation. Okay, okay, now let's again draw CS1. So this is your CS1, okay, this is your CS1, and the fluid is not crossing all the area of the CS1, right? It is only, let's say, till here. The cross section is only this much that the fluid is crossing. Okay, so in that case, will this capital A equal to the area of, so is A equal to area of CS1? The answer is no. This area is not area of CS1. Instead, it is only this much area. Okay. Okay. So in that case, now if you have understood this properly, let's write this term. So this is Vxyz in x-axis. What is that? This is given to be 15 meters per second. Okay. So this will be 15 meters per second. Let's not write the units. I hat. Okay. Density, let's say it is rho. Then Vxyz dot A vector. So the velocity vector is this, and area vector is this, right? So what would be V dot A? It would be, in this case, equal to minus VA. Okay, let's write this as, this is Vxyz A, okay, where this is area A. Okay, and this is multiplied. All right, and Vxyz we know is 15. With respect to the control volume, it is 15. Now we have to just write the magnitude, not the vector. So this is 15. Okay, now I had would cancel out with, will cancel out with I had, and will be left with this equation. Okay, so now from the knowledge of capital A and rho, I can find Rx. So Rx is 15 square rho A. Okay, I'm not further solving this, but you should get an idea that how can we solve this problem. Okay, I can put rho equal to the density value of water and A equal to the given cross sectional area, but that is just math. Okay, you have to understand the concept, and that's why I'm not further solving this equation. Okay, if you want you can do it. Okay, now this we got as positive. What does this mean? This means that the sign of the vector that I used in the negative x-axis is correct. If I would have got negative sign over here, this would have meant that the sign of this Rx that I have taken is incorrect. Okay, so let's say if I get this by solving, let's say I get Rx equal to minus 15 square rho A. This will mean that the sign of Rx that I have taken is incorrect. So Rx in this case will be in positive x-axis, or is directed along positive x-axis and not in the negative x-axis that I have taken. But we got positive here. This means that the sign of the Rx that we have taken is correct. Okay, so this is the direction of Rx. All right, now let's consider the second approach by using different control volume, and let's see whether we get the same value of Rx or not. Okay, so this was our control volume. Let's say this is CS1, this is CS2, this is CS3, this is CS4. Okay, now before this, let's I forgot to tell you that while calculating this F external x, we must have also considered the role of atmosphere pressure. So this is our P atmosphere. Okay, and then the F external on this portion would be nothing but P atmosphere, the pressure, atmospheric pressure times the area of the CS1. Okay, and similarly pressure here would be P atmosphere times the area of CS2, and here it will be P atmosphere times the area of CS3, and here it would be pressure times the area of CS4. Okay, but you can see from the symmetry of the control volume, the force due to pressure from this side, the force due to pressure from this side and the force due to pressure from this side will cancel out. Similarly, the force due to this side and the force due to this side will cancel out. Okay, so in such cases we don't consider the role of atmospheric pressure, because anyway it will get cancelled out in our problem. Okay, but still for completeness we should consider the atmospheric pressure also. Okay, all right, So let's consider the second approach. Now again you can say that there is a p atmosphere acting here, here, here and here, and again because of the symmetry the force on this part and the force on this part would cancel out. And the force from this part and the force from this part would cancel out. Okay, so we'll not consider the atmospheric pressure, the force due to atmospheric pressure currently in this problem. Okay, all right. Now let's again write the Reynolds equations, Reynolds transport theorem equations for mass and momentum. And we can see from previous approach that the equation from mass was not useful to us, so let's just write the momentum equation now. So what was the momentum equation? Momentum equation is summation over F external with a vector is equal to d by dt integral over control volume rho dv plus integral over control surface rho vxyz dot dA. Okay, so this was actually the summation over CSI rho vxyz dot A vector. I'm not writing CSI, okay, but it should be clear to you that this is in CSI and for that CSI only. Okay, so this was our equation, and for steady flows this would be 0. So we are only left with summation of external equal to summation over CSI rho VA. Oh, so I forgot one term here, Vxyz rho Vxyz dot A vector. Okay, let me just write it again, summation CSI Vxyz rho Vxyz dot A vector. Okay, all right. Now again, because we are required to find Rx only, the horizontal force, this is x, this is y, we are required to find the horizontal force. We'll only consider this equation in x-axis. So F external along x-axis equal to summation over CSI V xyz along x-axis rho Vxyz dot A vector. Okay, now what is the force along x-axis on the control volume CV? Oh, and one thing I was incorrect about. So although the pressure force from this side and this side will get cancelled out, the pressure from this side on the control volume and from this side on the control volume will not get cancelled out. Can you see it why? This is because the pressure force from air is acting on this plate and not on this fluid for this control volume. Okay, now because of that, the pressure force from air on this control volume is this one. On this one I don't have any pressure force from my air, and these two will get cancelled out anyway, so let's not take them. Okay, let's just take this value, this pressure force. What will be this pressure force? This will be nothing but P atmosphere times the area of this CS1. Okay, and this area is actually the area of plate. Okay, so this much area. Okay, and what will be the force from this side? What will be the force from this side? This will be nothing but the pressure the normal reaction from the plate. Okay, so let's consider that normal reaction as N. Okay, so now in the x-axis in the x direction, what is the total force acting on this control volume? This is nothing but P atmosphere times area of the plate minus N I hat, okay, equal to, now like we did before, we have to take only those surfaces where this Vxyz in the x direction is non-zero. So what are the control surfaces for which this value is non-zero? That is only CS1. Okay, so again this will be like V xyz x rho Vxyz, and what is this Vxyz dot A vector for CS1? That is minus Vxyz A. Okay, and what is the value of Vxyz? Okay, so if I so what is the let's first take this magnitude. So what is the magnitude of Vxyz along x-axis? That is given to you in the problem, which is 15 meters per second. 15 meters per second in positive I hat. Okay, and this is also 15, so this is 15 square with a negative sign times rho A I hat. Now this I hat will get cancelled out with I hat, and we will get the value of N. So N will be P atmosphere area of plate plus 15 square rho A. Okay, so I have taken N this side and this term this side, so this term going this side will become positive, and minus N going this side will become positive, and that's why this is like this. Okay, so this is our normal reaction. Now if but we had to find Rx. So this was our plate, okay, and if the plate is applying normal reaction and on the fluid, what is the force that the fluid will apply on this plate? From Newton's third law of motion, this is N. Okay, this is the force that the fluid will apply on this plate. Okay, and I was applying force, or the question was that you are applying force Rx. What will be the magnitude of this Rx for the plate to be stationary? So what will be this now? So it will be, so the total force acting on the plate should be 0. This implies N vector plus Rx vector should be 0. Correct? Now since N vector, this N vector was the, okay, this is this N vector that we find is along positive I hat. It's along minus I hat because I assumed this N to be directed this side. Okay, that's why this negative sign was there. So this is directed along minus I hat. So that's why this reaction from fluid on the plate will be in the along positive I hat direction. Okay, so if I just take this, F plate should be 0. Okay, now N on the plate, N is directed on this side, Rx is directed on this side, so N should be equal to Rx in magnitude. Okay, so this implies Rx is equal to, oh, and I also forgot the force due to the atmospheric pressure. So that will be P atmospheric times A of plate also. A of plate is given as AP. Okay. So although while deriving these kind of problems we forget about the atmospheric pressure, but the correct answer is only when you will consider this atmospheric pressure. Okay, so don't make mistakes like these. Okay, so Rx, so N is equal to Rx plus P atmosphere times AP. Let me just write it like this, plus P atmosphere times AP. So this Rx will be N minus P atmospheric times AP. And what was N? The magnitude of N was this, P atmosphere AP plus 15 square rho A minus P atmosphere rho A, P atmosphere times AP. This and this term would get cancelled out, and this will become 15 square rho A. And we can see that the value of Rx that we found from first approach and the value of Rx that we find from second approach, both values are same. Okay, so it does not depend upon what control volume you should take or you have taken. If you have considered the right forces for your problem, you should get correct answer for whatever the quantity you are finding from this Reynold transport theorem. Okay, all right. Next, let's consider another problem where the control volume is not stationary but moving with constant velocity. Now this is our problem from the book Fox and McDonald's. So let's first read the problem. So the problem states that the sketch shows a vane with a turning angle of 60 degrees. So this is, let's say, 60 degrees. It is already shown here. Okay, it moves at a constant velocity, at a constant speed, 10 meters per second. So it is moving with a constant velocity u equal to 10 meters per second. Okay, and receives a jet of water that leaves a stationary nozzle with speed v equal to 30 meters per second. So this jet is leaving this nozzle at a velocity of 30 meters per second. The exit area of this nozzle is given to you. So this area is given to you. Determine the force components that act on the vane. So the problem states that although the fluid is going like this vane is still moving with a velocity u, and now find the force components that act on this vane. Okay, now since our interest is to find force on this vane, the force components on the vane, I have to take a control volume. I have to take a control volume like this. Okay, I cannot take the control volume like this because then this ground is not moving with velocity u. So I have to consider the control volume like this. Okay, and you can see here that now as the vane is also moving, the control volume is also moving with the velocity with constant speed u. Okay, and this v vector is the velocity of the fluid, but this velocity is with respect to ground, with respect to some stationary observer here in the ground, and this u vector also is with respect to some stationary observer on the ground. Okay, so this implies that this velocity with respect to the control volume will be, let's just write it here itself. So let me just give you one example. So let's say A is moving with velocity VA and B is moving with velocity VB. Let's consider VB greater than or let's not write anything about v, the magnitude of v and vb. So the question is, what is the relative velocity of A with respect to B? So in that case, so what is the relative velocity of A with respect to B? Okay, so we just write this as the velocity of A with respect to ground. With respect to ground, ground means some, with respect to some observer on stationary ground, minus Vb with respect to ground. Okay, this is the formula that we use. Okay, and similarly the velocity of Vb with respect to A, let's not write, it's not the vector, so velocity of B with respect to A is nothing but Vb with respect to ground minus Va with respect to ground. Okay, so if this is clear, what is the velocity of fluid with respect to control volume? So velocity of control volume with respect to ground is u vector. Velocity of fluid with respect to ground is v vector. So what is the velocity of fluid with respect to Cv? That is nothing but the velocity of fluid with respect to ground, which is v vector, minus the velocity of Cv with respect to ground, which is u vector. Okay, so this is my velocity of fluid with respect to Cv. So the Vx yz is v minus u, and that formula, the formula for that we derived using Reynolds transport theorem for linear momentum. Okay, all right. Now if you consider about the forces on this control volume, what are the external forces on this control volume? So the one is the reaction force provided by the ground in the x-axis, so let's call it x, let's call it y, and the reaction force provided by the ground in y-axis, along y-axis. Okay, let's define the control surfaces as CS1, this as CS2, this as CS3, and this as CS4. Okay, now since atmospheric pressure is acting from all sides, we know that this will anyway get cancelled out, so let's not consider atmospheric force, the force due to atmospheric pressures. Okay, so that will get anyway, and that will anyway get cancelled out, so we are not considering atmospheric pressure now in our problem. Okay, all right. Next, let's just write the equations that we derived using Reynolds transport theorem for mass and linear momentum. And for that, again let the assumptions be steady state flow, uniform flow, and incompressible flow. Let me just write it somewhere here. So from Reynolds transport theorem for mass, with these assumptions in mind, I have summation CSI rho dot A equal to 0, and with linear momentum the equation that I have considering the steady state is summation of external equal to, considering these three assumptions, will be summation CSI V XYZ rho V XYZ dot A vector. Okay, and you can also see that gravity, due to gravity, a gravitational force is also acting downwards, that is equal to mg, where m is the mass of the total system. Okay, alright. Now since the unknown forces for this problem are Rx and Ry, which are directed along different axes, let's break this equation in two orthogonal axes. So F external in x is equal to summation CSI Vxyz rho Vxyz dot A vector, with this Vxyz in x axis and F external in y summation CSI Vxyz in y rho Vxyz dot A vector. Okay, now the force which is acting along x axis is Rx. So this will become Rx, and the forces acting along positive y axis are Ry minus mg. So this will be Ry minus mg. So let's mark this as 1, this as 2, and this as 3. Okay, now let's first consider term 1, which is summation CSI rho Vxyz dot A equal to 0. Now let's see the control surfaces. So these are my control surfaces, CS1, CS2, CS3 and CS. The fluid flow would be something like this. Okay, now if you see here, the way I have drawn the control volume, it's making things complicated, right? So I don't know whether it is going into CS1 or whether it is going to CS4, and again what area I should take. So instead of defining the control volume like this, the better way of defining control volume is like this. So if I draw it like this, then I draw it like this, and I draw it like that, this will make life easy. Okay, so let's say this is CS1, this is CS2, CS3, CS4 and CS5. Okay, now let's write what is rho Vxyz dot A on that control, on those control surfaces. So on CS1, there is no velocity. Okay, so this will not contribute to this equation. Okay, then similarly CS2 will not also contribute to this equation. So the surfaces that will contribute to this equation are CS3 and CS5. Okay, so, and since I am considering the same fluid, the same density, only one fluid, so this rho can be taken outside, and rho times something which is equal to 0 means that if rho is not 0, that something should be 0. Okay, so we are left with this equation. Now let the velocity, so it's given that the velocity exiting from the nozzle is V. It's not written that the velocity with which this fluid is coming towards the vein is V. Okay, so in that case I cannot write, so this was the velocity of the fluid at exit point of the nozzle. Okay, so I cannot write the velocity of fluid with respect to CV equal to V minus U on all surfaces, right? Okay, so let's assume that the velocity at this surface is V1. The control surface that I'm taking is CS2, so let's just write this as V2, and this is CS5, so let's assume that this velocity is V5. Okay, now with this information in hand, what will be this equation? This equation will be V2 times A2 and since this is an inlet, this will be minus plus V5 times A5 equal to 0, which I can also write as this. So V2 A2 equal to V5 A5. Okay, where A5 is the area of this surface. Alright, next let's take second term, which is Rx equal to summation over CSI Vxyz along x rho Vxyz dot A vector. Okay, now again, and for this term only CS3 and CS5 are going to contribute. Okay, so we can write this as, now since rho is only for one fluid, we can write rho outside. Okay, and for CS3 the velocity is the velocity O, so this is CS3. Okay, so I should have written it 3, let's not make confusions. So this should be V3 and this is V3. Okay, okay, so now for CS3 this is V3, so the velocity along x-axis is V3, rho is outside, Vxyz dot A is V3 A3, the area is also A3. Okay, the area of this part is also A3, so V3 times V3 A with a negative sign, because dot product will give me a negative sign, plus V5. Okay, so this will not be V5. Let's see here. So on this surface, let me just draw it again. So this is your CS5. Okay, this is your CS5. The velocity V5 is like this. Okay, so the velocity, I am considering velocity along x-axis only. Okay, for this part, so I have to resolve this V5 along x and y, and what's given is the angle 60 degrees. So it is given that this is 60 degrees, so this will be V5 cos 60 and this will be V5 sin 60. Okay, so the component of velocity along x-axis is V5 cos 60, okay, times vxyz dot a vector. Now a vector is pointing along this direction and velocity passing this cross sectional area is v5. So what is v5 dot a? That is simply v5 times a cos 0, which is 1, so it will become v5a. Okay, so I get Rx is equal to, this should be a3 and this should be a5, so it is v5 square cos 60 a5 minus v3 square a3 times rho. Okay, now the problem is nothing is given about a5 in this problem. Okay, so if it is not written, then we have to come up with some assumption. So let's assume that the velocity at this point and the velocity at this point is same, and if the velocities are same, if v3 is equal to v5, the areas will also be same. Okay, so in that case I can write a5 is equal to a3 and v5 is equal to v3. So wherever I see v5, I'll write v3, wherever I see a5, I'll write a3. Okay, and this becomes rho v3 square a3 cos 60 minus 1. Okay, or I can write this as rho v3 square a3 1 minus cos 60. Okay, and also in the problem nothing is given about the velocity v3. So let's also assume that the velocity with which this fluid is exiting the nozzle is the same velocity with which this fluid is entering this control surface CS2, control surface CS3. Okay, so in that case let's assume this is v vector, and thus vxyz would become u minus v vector, but this is vxyz for CS3. Okay, so now we know v3, which is v3. Okay, so I can write this v3 as u minus v. Okay, so this is minus rho u minus v square a3 1 minus cos 60, and this area a3 is area of cross section of the nozzle. So the velocity, let me again check this. So velocity of fluid, if let's say velocity of CV with respect to ground is u and velocity of fluid with respect to ground is v, then velocity of fluid with respect to ground will not be u minus v, it will be v minus u. Okay, okay, I can write this as, so if a vector minus b vector mod square is given, I can write this as a square plus b square minus 2 a dot b. Okay, and I can remove this dot product with the angle between vector a and b. So what is the angle between v vector and u vector? So the nozzle, the velocity of the fluid was v vector in the x direction, and the velocity of vane was u vector along x direction. So the angle between v and u is 0 degrees. So in that case I can just write this as minus rho v square minus u square minus v square plus u square minus 2v u, and this is nothing but v minus u whole square a3 1 minus cos 60. Okay, so this is the value of Rx using, and V and U are given to you. Rho you already know, A3 is the area of nozzle, and this value you already know. So you know Rx using Reynolds transport theorem, okay, for mass and momentum. Now let's find Ry. So similarly, now if I do analysis in y-axis, I should be able to find Ry. Okay, so now what are the forces along y? As you are okay, so we already argued that that Ry is along positive y-axis and mg is along minus y-axis. So this will become like this: Ry minus mg equal to summation over Csy vxyz along y rho vxyz dot a. So let's just write it, or let me just copy paste it. Okay, this is not required now. Okay, now our task is to find Ry. So this term will be contributed, only by the surfaces which have velocity vectors along y direction, y axis. Okay, so what are the surfaces that have velocities along y axis? It's only CS5, right? So the velocity times sine 60 is the velocity vector along y-axis for CS5. Okay, so only CS5 is going to contribute in this expression. Okay, so this will become, so vxyz y for CS5 is what? It is v5 sine 60. And what was v5? v5 was v3. And what was v3? v3 was v minus u. Okay, okay, and multiplied by rho. And what is vxyz dot a vector for that? That is v minus u a, because that is the outlet. So this becomes v minus u whole square rho sine 60 times the area. So actually this was a5, and we just assumed that this a5 to be equal to a3, and this a3 is the area of cross section of the nozzle. Okay, so we'll get Ry is equal to v minus u whole square rho sine 60 times a plus mg. Okay, so now we have the information about Ry and we have the information about Rx. So we have the information about all the forces that are acting on my vane. Okay, and since this Rx is found to be negative, this thing implies the direction that I have considered for Rx earlier is wrong. It is opposite to that. So actually Rx is directed towards minus x-axis and not towards the one that I have considered earlier for this problem. Okay, so this is the actual direction of Rx, and Ry is positive, so this is actually the direction of Ry. Okay, and the magnitudes are given by these equations. Okay, so now I hope this is clear that even if your system of interest is moving with some velocity, let's say u, you can still find the force vectors using Reynolds transport theorem. Okay, so Reynolds transport theorem is for the control volume which is either stationary or moving with constant velocity. Or we can also say that if the control volume is inertial reference frame, then we can use the Reynolds transport theorem equations to find various unknown quantities. Okay. Next, let's say if your control volume is accelerating. So let's say if your system, the system of interest is accelerating, you are left with no other choice but to take control volume which is also accelerating with system. Okay. So in that case, can we use these equations? We'll see this in the next lecture. Okay.